Thanks, Rowena, and thanks to GC Biotech for inviting me to give this presentation today. So today I'm going to talk about the power of fluorescence for quantifying biomolecules and give you some tips and tricks from our technical team who are based at DeNovix Inc. in the US. So I'm Andrew Jones, I'm the Market Development Manager for DeNovix. I'm based in the UK. So today we're going to talk through the comparisons between absorbance and fluorescence quantification. I'm going to talk a little bit about what the differences are, what the fundamentals are, and what are the advantages of each of those methods and when we should put them into practice. We'll also spend some time looking at what is the best practice when we're preparing these assays and running these samples. So what handling steps should we consider? What instrumentation do we need? How do we ramp up throughput? Those sort of things. So when I talk about absorbance, generally I'm talking about something like in this video, this is the DeNovix DS11FX Plus, and so we're talking really about microvolume UV vis absorbance, measurements and quantification of biomolecules such as nucleic acids and proteins. So in this example we pipette 1 microliter onto a pedestal, hit measure and wipe it clean. Historically this would have been done using cuvettes, but now microvolume platforms such as this are far more common. So the basics of absorbance, so we'll talk about absorbance as a comparison to the fluorescence assays that we'll come on to talk about later. So the basics of absorbance, the amount of light going through a sample is absorbed in direct proportionality to the concentration of the sample that we put onto the instrument and how far the light from the instrument travels through the sample. So we've got a little video here and you'll see that we have a sample on here and the arm will compress. So you see the light turning on, the arm will compress, and the distance that we talk about here is the distance between that upper and lower pedestal. And you'll see that this sets multiple path lengths for that sample, and we'll go on to talk about why that's important through the course of the presentation. But the distance between these two measurement surfaces is what replaces a traditional cuvette and sets the distance parameter for this equation. So if we know how much light of a specific wavelength passes through a sample, then that allows us to calculate the concentration of that sample according to the Beer-Lambert equation. So one of the fundamental properties of absorbance is it uses the inherent properties of the sample in order to do the quantification. And by that I mean that we don't have to have any additional kits or reagents that we add to the sample in order to do the quantification. Absorbance, as we've seen, allows us to use very small volumes of sample, so less than 1 microliter is possible with these methods. And it's a very rapid test, takes just a couple of seconds on this instrument. So the comparison or the contrast with fluorescence is that when we use fluorescence assays, it involves a fluorescence molecule binding to the target of interest. So we have to set up an assay, and this requires us to set up a standard curve alongside that assay. Volumes generally, it's variable because there are many different assays available. In this field with fluorescence quantification, it generally is between 1 and 20 microliters of sample, and usually around 200 microliters total assay volume. And that assay takes place in either thin wall PCR tubes like the one you can see in the picture here, or in microtiter plates if you're using a plate reader for higher throughput measurements. So for the basics of fluorescence, this is a fluorescent molecule. This happens to be fluorescein. And a fluorophore is essentially a chemical compound that once it's excited by light, it re-emits light. So to take a look at how this works, we have an excitation source, which could be an LED or a lamp of some sort. and that light hits our fluorophore, and we then have emitted light, and that emitted light is always of a longer wavelength, a lower energy, lower frequency light than that excited it. Now, one of the properties that makes this useful in quantifying biomolecules is that once this fluorophore is bound to our analyte of interest, in this example here is DNA, the fluorescence emission is enhanced. So by binding to the molecule of interest, and this depends on the assay and the formulation of the assay, once it's bound to the analyte of interest, the fluorescence emission is enhanced, and that allows us to discriminate between fluorophores that are in suspension and fluorophores that have bound to their target molecule. And this allows us to then quantify how much of that target molecule is in our sample. So I want to just, in order to sort of progress through the various aspects of fluorescence and what's important when we're thinking about hardware and assays, I just want to take you through some of the basics of how the excitation and the emission affects the quantification results. So on the left hand side here we see a tube that's full of our fluorescent assay, and the circle here just represents how many molecules are in there, and during the course of this you'll see them light up as we progress through this visual spectrum. So on the right we have this visual spectrum that goes, in this example, from 400 past 700 nanometers. And you'll see as we excite it with increasing wavelength light, more of those molecules light up in the assay. And this is to a point that it reaches a maximum excitation. If we go from the excitation maximum and we continue to increase the wavelength of the light, you'll see that we have a decrease in the number of fluorophores that are lighting up. So this trace that we have here is generally called our excitation spectrum, and it means that there is an optimum position or an optimum wavelength of light that will excite the maximum number of fluorophores in any particular maximum number of molecules for any particular fluorophore. This is a characteristic shape for each fluorophore. On the emission side, we also find that emission takes place over a spectrum with an emission maximum too. Now this isn't related to the wavelength that the excitation takes place at. This is basically the emitted light will always emit over a spectrum of wavelengths. So you'll often see data about a particular fluorophore represented something like this, with two traces and an excitation maximum and an emission maximum. And where we try to set our technology, or we try to set our excitation and the emission parameters of our technology, is around these maxima for both excitation and emission. And the importance of this is shown in this next slide. So what this slide will show you is, as we excite approaching that maximum, we'll see the difference in fluorescence intensity appear on the right hand side. So as we increase the wavelength, you'll see that the fluorescence intensity increases up to this maximum point, and then it decreases again as we go beyond that maximum and down to almost zero. And the important point here is that when we are choosing our hardware for fluorescence assays, it's important to try and get the excitation as close as we can to the maximum peak for the excitation of the fluorophore in order to get the maximum sensitivity out of the assay. So we can use assays that are not perfectly lined up with our hardware or our technology, but we have to accept then that we may have to sacrifice some of the sensitivity of that assay. So how do we decide when to use fluorescence? There are a few things that we need to consider for our particular situation. We need to look at sensitivity. How sensitive do we need our quantification to be? How specific do we need it to be? And we also need to consider things like speed and cost of the assay. And what are the protocol requirements? So we're doing something downstream with our sample. What are the protocol requirements of those assays? So talking a little bit about sensitivity and dynamic range, a number of factors affect this with fluorescence. So the choice of assays is important. Different formulations, different manufacturers have different assays which will have different sensitivities and different dynamic ranges. So it's important to think about our samples and how they fit into the characteristics of any particular assay from a manufacturer. Sensitivity is also affected by the volume of sample that we put in, so we need to consider that, and of course the assay used. So the number of fluorophores is really important. So when we talk about absorbance, it doesn't matter how much of our sample we use. 1 microliter or 2 microliters or 3 microliters will always give us the same answer. With fluorescence it's different because it's really quantifying the number of molecules in that sample. So the number of fluorophores, the number of molecules is important. And when we talk about sensitivity as well, we have to think about our instrument setup. As we just saw, the light source, the excitation and the emission filters are all important factors when we're looking at sensitivity. So to give you an idea of how these assays are arranged, these are the DeNovix assays that I'm showing you here at the moment. This is for double-stranded DNA. And in this assay family, we have 3 different assays. We have a broad range, high sensitivity, and an ultra-high sensitivity assay. And you'll see the broad range assay takes us from 0.1 nanogram per microliter up to 4,000 nanograms per microliter. A high sensitivity takes us down into the picogram range, so 10 picograms up to 250 nanograms per microliter. And we also have this unique ultra-high sensitivity assay, and this goes down to 0.5 picograms per microliter, and this is really used by people working on single cells, people on cancer studies, some forensics and entomology type studies. We've worked with people with this assay. So each of these assays has its own range, and likewise for RNA we have a assay range associated with this, and actually compared to our competitors in this market, we actually have a single assay here that covers a much wider range than the competition. And the advantage of this, of course, is that it just fits, more of your samples will fit into the range of this assay, so you don't have to go and dilute samples or choose another assay with a different range. So as well as sensitivity, we need to consider the specificity of assays. And one of the real advantages of fluorescence is that the kits are very specific to a single analyte. So if we're purely interested in double-stranded DNA, we can get a kit that specifically binds to a double-stranded DNA molecule and ignores anything else in that sample. So this is a big advantage in knowing specifically what we have in there. But the downside of that is that it won't give you any information on sample contamination. When we compare that to absorbance with UV-Vis, we know that UV-Vis won't reliably separate nucleic acids. So if you have RNA in a DNA sample or single-stranded DNA, then you can't do that reliably with an absorbance measurement. You can do that with a fluorescence assays or with a series of fluorescence assays. But what UV-Vis can do, and does very well, is it gives you the ability to detect contamination in your sample. So contamination through it may be proteins, it may be phenol, it may be salts co-extracted when you do your DNA or RNA extractions. So to take you through a little bit about contamination, wanted to show you this this phenomenon about nucleic acids and differentiating nucleic acids, because I think this is a really important thing in a lot of labs. So on the left hand side we have a sample that we're going to run here, and basically we have our microvolume sample going on, and we're going to run this same sample on both absorbance and fluorescence. So we have the absorbance measurement going on here, and you'll see that we've quantified it, and it comes out at 322 nanograms per microliter. If we take that same sample and we run it by fluorescence, we put our little PCR tube in, hit measure, and the concentration here is 214 nanograms per microliter. And remember, this is the same sample. And we look at the absorbance on the left hand side, and it looks like a great sample. It's a nice trace. There's no clue about other contaminating peaks, but obviously there's a big difference in concentration. So the difference between these measurements is due to the fact that this DNA sample has been spiked with RNA. So it has contaminating RNA of around 100 nanograms per microliter in it. And you'll see that because it's a nucleic acid, and all nucleic acids absorb at 260 nanometers, absorbance can't differentiate between the two, but the fluorescence measurement gives us a very specific measurement for our double-stranded DNA. Continuing with the contamination aspect of absorbance, we can also quantify, or we can also calculate purity ratios, and these purity ratios are a well-established technique, been used for many years, and they take the measurements at 260 for nucleic acids and also compare those with the measurements at 280 and 230 and create a ratio from 260 280 and 260 230. And the 260 280 is our ratio of nucleic acid to protein. And the 260 230 ratio, the 230 measurement is generally organic compounds like triazole, phenol, guanidine, HCl, guanidine, thiocyanate, things that are likely to come through from our DNA extractions or RNA extractions. And there are a set of well-established thresholds where samples are deemed either good or bad, whether they're inside or outside of these thresholds. And just to give you an idea of how this looks in practice, I took another measurement sample here. You see this is just measuring on the DS11, and you'll see the trace on the left-hand side doesn't look great. So it highlights that sample with a yellow triangle, and when we click on that triangle, it gives us all the possible causes and solutions to what is wrong with that sample. So it identifies that it's a poor sample, it highlights it with this yellow triangle, and behind that yellow triangle is advice on what to do with our sample. So what are likely to be the problems? Is it methodological, or is it actually physical contamination in the sample? So absorbance gives us this qualitative measurement as well as a quantity, but fluorescence will give us a very specific measurement. So absorbance and fluorescence, they're different methodologically and distinct, but very much complementary quantification methods. So when we compare the two, we've seen that absorbance is not analyte specific, whereas fluorescence has a very high degree of sensitivity, specificity, I'm sorry. So that highly specific nature of the kits means that we get accurate results for our analyte of interest only. Absorbance can be a very sensitive measure. The DS11 that we saw measuring those samples can measure down to 0.75 nanograms per microliter of double-stranded DNA. But fluorescence is a much more sensitive technique. So it's highly sensitive, can measure down to 0.5 picograms per microliter of double-stranded DNA. That's when you're using the ultra-high sensitivity DeNovix kit. Absorbance has a very wide dynamic range. So we saw at the start of this presentation that the DS11 compresses our DNA sample, or our sample that's on the pedestal, and by compressing the sample it increases the dynamic range of concentrations that you can measure over. And because we have micron level control over the distance that it can travel, we can compress that to very small distances and increase the dynamic range. So this is actually the widest dynamic range of anything on the market. The fluorescence assays also have a wide dynamic range, but it's kind of a different level to absorbance. So the fluorescence assays can go up to 4,000 nanograms per microliter when using the broad range kits. Absorbance can give us contamination guidance, as we saw, whereas fluorescence doesn't have that ability, unless of course we use multiple kits for DNA, for RNA, for protein to really to really identify exactly what's in that sample. And of course with absorbance we don't have any assay costs or time associated with, or any real time associated with setting up assays. And for fluorescence we need to purchase kits and we need to set up those kits. So there is a cost and a time factor involved in fluorescence. So the question is, when do I use fluorescence? Well, why would you choose fluorescence? One of the answers is when your protocol tells you to. So that sounds a bit glib, but if you're doing something like next-gen sequencing, there are stages in that protocol, in that workflow, where it will tell you to use absorbance, and there are stages where it will tell you to use fluorescence. And that's because it needs either a very specific measurement of your analyte, or you need to be able to identify any particular contamination that is in your sample at that time. So if you have sample contamination, for example RNA or degraded DNA in the sample, you might want to use fluorescence to get a specific measurement. Also, this is particularly relevant to proteins and using things like Ripper buffers. If your buffer composition absorbs highly at the same wavelength as your sample, then UV-Vis may be inappropriate for that particular sample. So you may choose fluorescence rather than absorbance in those situations. Clearly, if you have low concentration samples beneath the sensitivity of absorbance, you'd want to use fluorescence. And sometimes when you're looking for higher throughput, fluorescence can be an easier assay to automate. So just moving on, the final section of this is really to talk about best practices. So if we've decided we want to use fluorescence, what are the best practices? What are the things we should consider and look out for when we're running samples or when we're setting up our lab for to run fluorescence assays? So first of all, best practice, the hardware selection is important. So we've seen we've seen earlier in the presentation the effect of hardware choices in terms of excitation and filters. So your instrument choice will be important, and that's often based on availability, the model, what is installed on that instrument. So if you already have an existing plate reader, for example, what filters, what light sources are available. Do they allow me to run the assays that I need to run for my particular samples? When we're thinking about instrument choice, we're thinking about throughput. If we're only running a few samples at a time, it's unlikely that we'll want to use a plate reader. We'll probably want a single tube system. And we can think about speed, space, budget, all the common things that we need to think about when we're making an instrument choice. But as we saw earlier, it's really important to ensure that the correct light source is available for your assay. Otherwise, you're going to be compromising on sensitivity. So there's a nice little guide that GC Biotech have put together, and I'm sure they'll email this through to you if you drop them a note. And this just highlights, for all the different sample types, the dynamic range of the different assays and the requirements in terms of hardware to run those assays. So you'll see in the middle here we have the 3 double-stranded DNA assays and the RNA assay on the end. And you can see in the middle all the spectral properties of the assays are all laid out here, the excitation and emission requirements, the fluorometer channel. So the DeNovix instruments are all 4-channel fluorometers. So we have a wide choice of LEDs and emission excitation choices that you can use, which just opens up and expands the number of assays that you're able to run. All of our assays here are also compatible with microplate readers, so they can be used in single tube systems and they can be used in a range of microplate readers. I would always recommend, if you have one already, you just need to check, as I mentioned, the excitation source and also the excitation filters and the emission filters, and check that they're just compatible with the spectral properties that we see in this table. And all of our kits are available in either 250 or 1000 assay options. So our fluorescence range, as I mentioned, these are all single tube, but you can also use our assays on plate readers if you have one of those. So we have, this is the DS11, and the DS11 FX and FX Plus are our fluorescence instruments. So these combine microvolume cuvette and 4-channel fluorescence all in one instrument. So we have that integrated. I know that a lot of people already have a DS11 in their lab. DS11 is the absorbance only instrument. That can be upgraded very easily and very inexpensively with just this additional module here. It's in the center image. So that just plugs in by USB and it will automatically upgrade your instrument to full 4-channel fluorescence. And we also have a standalone instrument that for fluorescence, and this is called the QFX. So moving on from instrument choices, talk a little bit about assays and the standards that we need. So some of the best practices when we're dealing with assays, it's really important to know that many assays are broken down by ambient light. So you need to protect the dyes from the light, and that is when you store them, when you use them, and with any incubation times, it's a good idea to incubate these assays in the dark, so maybe in a drawer or just covered with foil. It's also worth checking if you're using any. It's also worth checking that the buffers that you're using in your samples are compatible with the particular assay. Does your assay cover the dynamic range? The dynamic range of the assay cover what you expect your sample concentrations to be? Now, many of the assays allow you to put in different volumes of sample to extend the range of the assay, either at the lower or the upper range. So standardly you would use 10 microliters in these quantification assays, 10 microliters of sample. But most of these assays allow you to use between 1 and 20 microliters, which just shifts the upper and lower range of the quantification range for those assays. As these are indirect measurements, as in we're binding this fluorophore to our analyte of interest, we need to create a standard curve. Now, most assays come with a standard curve that they recommend, and some either DNA or RNA or protein standard to make up that standard curve. You've got to make sure that those concentrations are appropriate for your sample, but perhaps more importantly, is the source of that standard appropriate for your sample? So they're kind of generic standards. So, for DNA there'd be something like calf thymus or something similar to that. It might be if you have a very say GC rich sample, that actually using the standard that's supplied with an assay kit isn't really appropriate, and you should make up your own standard, but that's something you need to test empirically. It's also more important when you're using fluorescence. It's really important to be careful with pipetting and to use an appropriate volume pipette. And the reason for this is that the fluorescence yield of a particular assay is going to be related to the number of fluorophores in that sample. So you just need to be careful about pipetting a similar amount, the same amount between your standards and each of the samples, so that you can compare them to one another. And treat everything the same. Treat your samples and your standard as exactly the same. So prepare them at the same time. Use the same reagents when you're preparing them. And just moving on, when we are measuring our samples, there's a few things to consider. Make sure you bring all the reagents up to room temperature if you've stored them in the fridge. So make sure everything is room temperature before you set them up. Mix them well, vortex all of the reagents and the samples before you measure them, but avoid bubbles. Bubbles can refract the light and cause anomalous results. Make sure you measure the samples and the standard curve at the same time. Now, a lot of software, including our software, will give you the option to save a standard curve and reuse it at a later date. We always strongly recommend that people don't do this. The standards for our assay, the standard curve is only a 2-point standard curve, so it's a 0 or a blank, and a top standard. So actually creating the standard curve only takes a few seconds. So we always recommend that you use a fresh standard curve, but we do understand that some people like to save those curves and are happy to accept that there may be some systematic error when you save a standard curve and then create the samples at a later date. And just a word of warning really, or a final word of warning perhaps, is that fluorescence is reported in RFUs, so relative fluorescence units, until it's compared to a standard curve and then converted into a concentration. The RFUs are relative. You can't compare those raw values between instruments. So don't use those raw values as a comparison across labs or across instruments. So just in summary, fluorescence and absorbance are very much complementary methods in the lab. It's important to be able to do both, and both of them give you different things and different abilities and a different view on your sample. Fluorescence will give you this highly sensitive and specific quantification of your sample, whereas absorbance will provide you with a rapid quantification, is accurate for clean samples, but when there is contamination, it will give you information about that contamination as well. So really the key point is that for optimum sample quality control and for greatest flexibility in the lab, the best option is to be able to combine fluorescence and absorbance measurements. And that will give you the specific quantification of fluorescence along with the contamination detection of absorbance. So DeNovix instruments and our fluorescence quantification assays provide an integrated platform for total sample quality control by combining these two different methods into one instrument. And I know that GC Biotech are happy to arrange in-lab demonstrations for anybody who wants to try these out in their own labs on their own samples. And that's my final slide. I'd like to say thank you very much for logging in, and if there are any questions, I'd be happy to take them.
Well, thank you, Andy, for this presentation. We have some time for a few questions, and we have one question in the chat box from Ferry Wijnhoven. Is it possible to take the sample from the UV-Vis part and use it for the fluorescence part, so to save precious microliters of your sample?
Yeah, thanks for the question. It's a good question. So that is non-destructive, so you can recover that sample if you have a very precious sample and you don't have any spare. Obviously, you want to make sure that you're cleaning the surface particularly well. But you could theoretically take that microliter off the UV vis pedestal and add that to a fluorescence measurement. The other option is that you can use even smaller quantities on the UV vis side, but you just have to be very careful with your pipetting to make sure that the sample is actually deposited onto the surface.
Great. Thank you, Andy. Another question. Could the instrument identify contaminants by spectral analysis?
Oh, okay, thanks. So basically we can, the contamination detection that we put in place on the DS11 is really based around things like purity ratios, and spectral analysis is confined to checking for things like negative spectra. So the spectral deconvolution that you sometimes see in the market, we find that we've looked into that significantly over the years, and our feeling on that is really it's kind of a black box implementation, and the quantities of contaminant required to trigger that spectral analysis and contamination correction is really too large to be useful in a practical setting. So we chose not to go down that route, and we really prefer taking the approach of combining fluorescence and absorbance to do that. So we don't use the kind of spectral deconvolution for contamination detection.